Shall I start with an introduction?
Oh, sure. You're welcome. Sure.
Yeah.
Yes.
Mr. Govind, thank you so much on behalf of everybody, for accepting this invitation. It's such short notice, and warm welcome. Okay. And for the members attending today's meeting, I'm sure most of you would have heard of Mr. T.K. Govind. He's a very senior faculty at Medtronic, been there in the company for ages, I think for more than a few decades together. But he's more importantly known and more popularly known as a very good teacher and troubleshooter for pacemaker, functioning and programming cycles. All of us, at some point or the other would have heard his lectures, as electrophysiologist or as cardiologist. So I heard Mr. T.K. Govind sometime in 2012 when I was doing an EP fellowship, and he was the one who introduced pacemaker timing cycles to us. And I was amazed then, and I'm still amazed now. I've heard his lectures several times, and each time there's something new to learn. I'm sure when Nikhil approached, for requesting a class on this, I had to either prepare a PowerPoint or I could ask Mr. T.K. Govind to do this, and I was sure that he would do a great job because he's been doing this for so many years, and I'm sure everyone will benefit from his teaching. Okay, over to you, Govind. Thank you so much for accepting today's invitation.
Thank you, sir. Thank you so much for that very generous introduction. Now I'm a little scared, before that, so much of preamble, then I have to live up to that expectation, which I will try to. And then, yes, once again, thank you very much for recommending my name for this presentation. And I would like to thank Dr. Nikhil for organizing and coordinating this and getting me as a part of this team for this presentation, and welcome all the participants. So we planned it as a two-part series. Today we are going to go through the basic technical concepts and the single chamber timing cycle. And on Sunday we will go through the more interesting dual chamber timing cycles and some bit of troubleshooting as well. And I'm sure most of you are definitely familiar with a lot of these technical concepts. Only thing, probably it has not been discussed in a very structured way to you. So this would be probably that will be the difference, which you would know. So I'm probably putting it together in a structured way. And I would request Dr. Manish to interrupt at any point in between to talk about the clinical implications or relevance of whatever technical aspect that I'm talking about. So please do interrupt me as and when you feel that it is appropriate, sir. Okay, so yeah, we start. So all of you are familiar with the pacemakers. Right, so there is, I'm not going to describe the basic pacemaker, but you know that it is essentially an electrical circuit where there is a battery and then the lead is placed inside the ventricle and electrons come through that. Yeah, electrons come through the conductor electrode and get delivered at the tip electrode, which is usually called as the negative electrode or the cathode. And the circuit is complete only when these electrons return back to the anode. In this case, in a unipolar system, which you don't use these days, it will return through the body tissues just like any other unipolar electrical system. And yes, in this, you recognize that the can is acting as an active electrode, in this case anode. And there is a little bit of disadvantage associated with this. Most of the young cardiologists probably would not have had an opportunity to interrogate a unipolar pacemaker, because currently what you are using is all the time bipolar. Yes, there could have been some epicardial implants which are generally unipolar. And then yes, if you had the opportunity, sometimes it results in a pocket stimulation while it is also stimulating the myocardium. So that's a little bit of a disadvantage. These days you don't use it at all. And when it comes to the lead itself, it is just like an electrical wire, which is made of a multi-stranded coil covered by an insulation. And this multi-stranded coil, it makes it as a floppy wire so that it is moving with the heart comfortably. That is because it is so floppy that at the time of implantation, you insert a stylet to make it a little stiffer to be able to control that. And the advantage of the multi-stranded configuration is that this is anyway a mechanical wire which is made by man, and then it is liable for fatigue, and over the years, it might undergo metal fatigue and it might fracture. So if it is multi-stranded, then a few of these wire might fracture, the other would still be intact. So a pacemaker dependent patient will still be safe. But when the patient comes for a regular follow-up, by observing the change in impedance, you can suspect a lead issue. And if it is confirmed, then you may plan to change the lead. But if it is a single wire, if it breaks, then your pacemaker dependent patient is in problem. And that's the unipolar system. And as I said, what you use today is all the bipolar system, where the can is not acting as an electrode anymore. Both the anode and cathode are there in the pacing lead itself. So the inner electrode, just like a unipolar one, has an insulation that ends at the tip, which is in this case placed in the right ventricular apex, and the current returns through the proximal electrode, which is the anode, which is the outer electrode of this pacing lead, and that has one more insulation on this. So in the older days, about 25 years back, there was a predominant use of unipolar leads because bipolar leads were a little thicker in diameter. But today the bipolar leads are fairly thin, so nobody opts for a unipolar lead, although they are still available. But there is a couple of advantages associated with this. I'm sure you recognize this straight away. One is the can is not an active electrode, so it is not going to stimulate the pocket while it's stimulating the heart in those occasional patients. And another important advantage is that because it's bipolar, and if there is a fracture that develops, and the most likely place the fracture can develop for the conducting wire would be at the junction of the clavicle and the first rib, where there could be some mechanical stress. If that happens, what will get affected first would be the outer insulation, and this mechanical stress would further transmit into the outer electrode, and logically it's the outer electrode that is likely to get affected first, whereas the inner insulation and the inner electrode may remain intact, and in which case we can still convert this pacemaker into a unipolar configuration so that you don't have to rush in for an emergency lead change. And the modern pacemakers are capable of measuring impedance constantly while it's pacing. And if there is a fracture that happens, we will discuss about that in greater detail, but I'm sure you know this, there is going to be an impedance change that might go out of range. And the pacemaker itself automatically convert itself into a unipolar configuration. And when the patient comes for, he would not know that because he's not going to be symptomatic, but when the patient comes for a regular follow-up, the programmer screen, the home screen, will pop up a warning stating that there was a polarity change because of a suspected lead issue because of lead impedance. And you may want to investigate more thoroughly. And if it is a true impedance change because of a lead fracture, then you may ultimately want to change the lead for that patient. So that's the advantage of the bipolar system as it exists today. And then, yes, we are passing current from the pacemaker, which is derived from the battery. So the battery provides the voltage, which is kind of a force that pushes electrons across the circuitry. And then it is passed through the wire, just like the water is being passed through the hose pipe in any water hose system. And the water can be imagined as the flow of electrons through this circuit. So the current is the actual measure of the flow of electrons, and this is denoted by the symbol I, and then the unit of measurement of current, as you know, is ampere. And in pacemakers we deal with milliampere current, so it's usually milliamperes. So by increasing the voltage, we can increase the flow of the electrons, just like in a hose in a tank. When you open the tap, it flows more forcefully, let us say. And then the whole thing is controlled also by the impedance, which also indirectly controls the flow of electrons. So there has to be a certain amount of reasonable resistance for it to flow in a certain direction, and that is what we measure at the time for a follow-up. And the current pacemakers constantly monitor this impedance by a periodic measurement as well. And so this impedance is a sum of several other impedances that happens. The sum of these, the components of these impedances are, one is the impedance So by design, companies make it as a low impedance conductor so that all the electrons that start from the pacemaker battery is able to reach the tip with least resistance. That means if I give 2.5 volts from the battery, then at the lead tip I want to deliver close to 2.5 volts. But if the impedance is higher at the conductor, then a lot of it may be wasted as heat, which we do not want. So by design, the conductor electrode is usually will have a very least resistance. And then the lead tip electrode also provides certain amount of impedance, and the interface, there is a little bit of impedance for the flow of electrons into the myocardium. And then there is a little bit of polarization that happens at the lead tip. So that also affects the flow of electrons. So what we measure at the time of implantation and at the time of follow-up is a total of all these impedance. So essentially, we should have a lower lead conductor impedance, which is by the design, and also lower interface impedance, but a slightly higher, polarization impedance. So this makes the, impedance, total impedance slightly somewhere between 500 to 1000 or 1500. So when this impedance is slightly higher, when the conductor is intact, then the current drain becomes less. And that is what is determined by the Ohm's law, which you all are familiar with, which we all studied in the middle school, and that's what it is. So voltage is a product of current and the resistance. And if we know two of these values, we can calculate the other value. For example, if we want to calculate the current outgo given the voltage and resistance, we divide the voltage by the resistance. And today's pacing systems, you don't have to measure all these, because both at the time of implantation and the follow-up, the programmer gives all these values. So we need to just get used to relate to those values. So that means that going by this one, current is the division of voltage by the resistance. So that means if the resistance is higher, then the current outgo becomes lower. When within normal limits, when the current outgo is lower, the energy outgo from the battery is going to be lesser. We will see some more details of that. And then the battery is expected to last a little longer for this patient. But if this resistance becomes significantly higher, then very low amount of current is flowing through that may not be adequate to capture. And that is what happens usually when the lead fractures. Right, so and then the impedance is going to be higher. So this is the total of the impedance that we talked about, the total combination of all the factors, other factors of the impedance. The normal impedance in a typical pacing system is between 200 ohms and 100 ohms, and it is not exactly the same at all times. Usually you find it's between, say, 500 to 1500, and these days you also have what is called as the high impedance lead, where the tip of the lead is designed in such a way that it provides higher polarization impedance, so that it reduces polarization, so that the pacing efficiency is better, meaning the lead diameter is made smaller, but the surface area is larger by making a porous electrode. So they are generally having a slightly higher impedance. So that's more towards 1000 and a little more than that. And it's not a good idea to poke around to get a higher impedance. But if you get a relatively high impedance of, let's say, 1200, and if your pacing threshold is good, it's worthwhile accepting that. So that's the thing. But when a patient comes for a follow-up, if you find a significant abrupt change of impedance of 30% or more or less, then it is worthwhile investigating that lead integrity closely. And then by this, when the impedance is lower than 200, it denotes an insulation break. So what happens in this case is that when the outer insulation breaks, when the electrons are flowing through the electrodes, then this can seep out of the break into the body tissues and the liquid or the fluid, and then it would cause a lower impedance. So the system becomes low in its impedance. So consequently, it causes a higher current drain. This pacemaker patient with a lower impedance with an insulation brake may not report with a loss of capture because still current is flowing at the tip. But whereas when the impedance is above 2000, typically when there is a fracture, it happens. And usually it's not even 2000, it's something like 4000, 5000 or upwards of 10,000. That means there is a total fracture between the proximal end of the conductor and the distal end of the conductor. So no current flows through that. And so these patients usually report with a loss of capture and hence symptoms. But as I said, the current pacemakers monitor the impedance and give a graph on the home screen of the programmer. You can observe that as long as it is stable, and we can assume that the lead is in good condition, and when thresholds are good, that is good. But as I said, when there is a sudden change of impedance of more than 30%, it's worthwhile investigating that lead a little more carefully. Yeah, so that's about impedance and Ohm's law. And then when we are stimulating with this kind of a system, the pacing system allows you, as you definitely know, you to program an output in terms of voltage, and it also allows you to program a pulse duration. These two are related, which we will discuss about in greater detail. So in this system, we have programmed an output of 5 volts, and we decide to, let's say, pace at a rate of 60 beats per minute, which means we want to pace the heart at every 1 second. And when we convert second into milliseconds, it's 1000 milliseconds. So we deliver a 5 volt output at a duration of 0.5 millisecond, which is 1/2 of 1,000th of a second. We start the pulse, 0.5 milliseconds later, we switch off that pulse. And then the pacemaker, as you know, has a clock. It runs for 1000 milliseconds, and at the end of 1000 milliseconds, it delivers the next pulse, and so on. And this is the amplitude, and this is the pulse duration, and the duration of the time between 2 pulses is the rate at which you are pacing the heart in terms of time. In this case, it's 1 second, in other words, 1000 millisecond. I'm sure you know this. Just to put it in the context, I'm relating to that, describing that. So here we would like to look at one pacing pulse in a little more detail to understand the energy outgo, etc. So now let's assume that we are delivering a pulse at an output of 2.5 volts, and we are delivering it for a duration of 0.5 millisecond, which is usually the nominal pulse duration in most pacemakers, 0.4 or 0.5 milliseconds. And then we measure the impedance. Impedance is not in our control, so we measure the impedance of this pacing circuit. It works out, it happens to be 500 ohms. Now, by applying Ohm's law, we can calculate what will be the current outgo. In this case, the current is voltage divided by resistance. So it is 2.5 volts divided by 500 ohms. And when we calculate the current, it's 0.005 amperes. You multiply by 1000, it's 5 milliamperes of current that is delivered on this output of 2.5 volts. And yes, so we can also calculate what is the energy that is drained from the battery with this. So which is a multiplication of a power, which is voltage multiplied by current, and that's multiplied by the duration for which we are delivering each pulse. So in this case, it will be 2.5 volts and 0.005 amperes, and then in this case 0.005 seconds. We can calculate the energy outgo in this. So now this will work out to 6.25 microjoules. So that's the small amount of energy that we are delivering. So at this point of time, let's say for some reason we want to double the output, let us say just because the threshold has gone up for this patient, then we may want to calculate what the energy outgo is. But imagine, remember that we are increasing the output or we are doubling the output, 2.5 to 5 volts. A common sense, easy calculation indicates that the energy outgo is expected to double, but it would not. It will become 4 times of that because of the behavior of the Ohm's law. So if we revisit this formula, we can actually, replace current by applying Ohm's law, which means that V is equal to IR. So it is V square T by R, right? So in this case, V by R is the current. So it becomes V multiplied by V square multiplied by time, and we need to divide by R. So in this case, the output of energy is changing by the square of the voltage. So when we double it, the actual energy outgo becomes 4 times. So why I am emphasizing this so much is that there are occasions when we want to increase the output, probably because of a higher threshold that the patient reports with. So then, yes, we need to be safe for the patient, but just blindly increasing the output to 2 times what it is existing might result in an energy outgo of 4 times. So instead of that, one option could be to consider checking the threshold one more time at a higher pulse width. So we might get a lower threshold. So in this case, if the threshold was, assume that it was 2.5 volts was the threshold, and if we increase the pulse width to 0.8 millisecond, and then check the threshold, it is likely to be below 2.5. And then at that pulse duration, we can increase the amplitude reasonably so that the total energy outgo is reasonably controlled, and it's not as high as while it is being doubled at 5 volts. So I guess that makes it clear. Then I'll go on further. So that's an important point that I wanted you to keep in mind. And then, as I said, there is a relationship between the output that we are delivering in terms of voltage or current or charge, and you can also relate it to energy, to the duration for which we are delivering the pulse. And that is what is the relationship, which is the strength duration relationship. And in a pacemaker, we generally control the voltage. So we can imagine this to be a voltage to duration relationship. So which is the intensity of the voltage or the amplitude of the voltage that is required to capture a non-refractory myocardial tissue. And this is dependent on the duration. It varies according to that. So that's what is the strength duration relationship. And if you vary the voltage, the threshold is different. And if you vary the pulse width, the threshold is different. And the behavior is like this. It's like a curve. And in this picture, the strength duration relationship curve, which has 2 components, which is Rio base voltage and the Kronaxi point, which we will discuss in a little more detail. The vertical axis represents the voltage and the horizontal axis represents the pulse width. And what is the Rio base voltage is? Rio base voltage is the minimum voltage threshold that we obtain when the pulse width is infinite. In a pacemaker, there is a limit to what pulse width that you can set. So assume that we are setting a pulse width of 2 milliseconds, and then we check the amplitude threshold. And at some point, we get the amplitude threshold. In this case, it works out to be 0.5 volts at 2 millisecond pulse width. And then we want to measure what is the Kronaxi point. And this is also called as the Rio base voltage, which is also referred to as a fundamental threshold. And we double the voltage, and then we fix the voltage, and we don't change the voltage. We gradually reduce the pulse width, and we determine what is the pulse width threshold. In this case, when we fix the voltage and we reduce the pulse width here. When we reduce the pulse width, in this case, the pulse width works out to be approximately 0.3 milliseconds. We can similarly calculate different voltage threshold for different pulse widths. Similarly, keeping the amplitude constant, we can determine the pulse width threshold for different voltage amplitudes. So it is common sense to imagine that when the amplitude is higher in terms of voltage, the pulse width threshold is expected to be lower. There is a limit to that. Similarly, you can increase the pulse width, and the voltage threshold will gradually come down up to that minimum point, which is the Rio base voltage. And no matter how much you increase the pulse width beyond that 2 milliseconds in this case, it would not go any further. So each combination of amplitude and pulse width on the curve is a threshold point. But then why is it important at this point, chronaxis point? That's what we want to examine. So yes, let's assume that we measure the impedance of this pacing circuit that happened to be 500 ohms. Then at chronaxis point, it is 1 volt and 3 millisecond. We can calculate the energy outgo by applying the formula that we discussed in the previous slide. So in this case, at Rio base voltage, which is 2 millisecond pulse width, 0.5 volt amplitude, and 500 ohm impedance works out to an milliamperes, that is current outgo of 1 milliampere. So this will work out to an energy outgo of 1 microjoule, which is a threshold point. Then we can also calculate the energy outgo at the chronaxis point, and our chronaxis point is 1 volt, and the pulse width threshold worked out to be 0.3 millisecond. So when we apply Ohm's law, in this case, the current outgo is 2 milliamperes. Then the energy outgo in this case is 0.6 microjoules. This is also a threshold point. This is also a threshold point, but you can see that the energy outgo at the chronaxis point is less than what it was at the Rio base point. So chronaxis point is the sweet spot where the energy outgo is the least. So if you want to scientifically test when a patient comes for a follow-up, that is what we have to do, but that's not possible because your department is too busy, so you cannot do that on every patient. But then in a well-implanted system, the chronaxis pulse width usually is between 0.25 to about 0.5 millisecond, and that's why most pacing systems have a nominal pulse width of 0.4 to 0.5 millisecond. And in fact, the current generation Micra pacemakers have a pulse duration nominal of 0.24 millisecond. So that's the importance of this chronaxis point, and this can be a reference point based on which I can program a two-fold amplitude to get a two-fold safety margin, or at this point we can program a three-fold increase in the pulse width, which is 1 volt at about, in this case 3. We can increase the pulse width to about 0.8 milliseconds. So either of this is okay, which will give a two-fold safety margin. But in this case, if we increase the pulse width beyond this point, then we are reaching the flat portion of the Rio base curve, or flat portion of the strength duration curve, and it is not going to be more efficient. It's going to increase energy delivery, but then our threshold will not come down. And so also is the case, we can take a significantly low pulse width, like in this case 0.25 millisecond, and then in this case the voltage threshold might work out to about 1.5 volts, and then the energy goes still more, but then the chronaxis point is the sweet spot. That's the scientific point behind this. But then because the chronaxis pulse width, as I said, is between 0.25 and 0.5 milliseconds in most pacing systems. At a nominal pulse width of 0.4 millisecond, we measure the amplitude output and program an output twice of that, which is reasonably good for most patients. You may have to, look at this pulse width more carefully when the patient comes back with a slightly higher threshold, where you may want to check the amplitude threshold at a slightly increased pulse width, and you can increase the amplitude at that pulse width a little more so that you maintain a two-fold safety margin, but reasonably conserve the energy outgo from the battery. So that's the importance of keeping the strength duration relationship in mind while we program the output for a pacing system. Okay, so if we were to work out energy strength duration curve, that might look like this. So yeah, so the heel portion of that will be the least one. That's what it represents. Okay, a little bit of a note on the pacemaker battery. So current pacemaker batteries, of course, the most recent pacemaker batteries are slightly different one. The conventional batteries are lithium iodine battery. So this lithium iodine chemistry based pacemakers will provide a voltage of 2.8 volts. no matter how big or small the battery is, the output that will come from that cell will be 2.8 volts, which is also called as the beginning of life voltage, and the current annotation is actually beginning of service. It's called as a BOS. And then gradually, after connecting to the lead inside the patient's heart, it lasts for some amount of time, and then it reaches a certain voltage, at which point we declare electric replacement indication, which is also referred to as ERI. Sometime even further below that, then it is said to have reached the EOL, or end of life or end of service. So some companies declare EOL based on the voltage. So in Medtronic, after it reaches ERI, and it's not exactly 2.6 in all the pacemakers, it is around that. It varies by the model, and it also varies from company to company to some extent. And then 3 months after the pacemaker reaches ERI, the pacemaker will function well for 3 more months at nominal outputs and rate. So that's why when the pacemaker, even though it's a dual chamber pacemaker, at the time of ERI, it will shift to VVI 65 for Medtronic, and it's different for different companies. So at a rate of 65, at a nominal output of 3.5 volts, the pacemaker will last for 3 months. But if the threshold is higher, and if you have programmed output more than 3.5, you can expect it to last for less than that. But then that's a very conservative longevity. In most cases, in Indian settings, we have seen that the pacemaker would actually last for 6 months to 1 year longer after the ERI, which is reasonably safe. But yes, it's a good idea to consider changing the pacemaker within 3 months after it is ERI. So when the patient comes for a follow-up on interrogation, the programmer tells us on what date and time the ERI trip occurred. So now you know when it occurred, so you have a fair idea about how much time that you have on your hand to be safe for the patient before you change the pacemaker. So that's the time that you can consider changing the pacemaker. And yes, and there is another factor that you may need to keep in mind, but then that's not so important today, because everything is determined by the programmer, and you get those values. Battery also has an impedance. So lithium iodine battery typically has a compartment of lithium and an iodine, and then separated by a semi-permeable membrane. And initially, it has a very low battery voltage, about of the order of 100 to 200 ohms. And when you connect it, the current flows through that. Inside the battery, it forms a compound, lithium iodide compound. It builds up over a period of time that gradually increases the impedance of battery. And that's why the battery voltage comes down over a period of time. And at the time of ERI, it will be usually about 3,000 to 4,000 ohms. When it reaches EOL, it is typically about 5,000 ohms. But we don't declare ERI based on the battery impedance alone. A lot of things are taken into account, including the voltage and the battery impedance, and the programmer tells you. So it's a good idea to go by the programmer recommendation, assuming that your threshold is good and the output is less than the nominal and not more than that. So that's the battery. So this is the typical battery depletion curve. 2.8 gradually drops to 2.6 while the impedance of the battery goes up. And between ERI or RRT and EOS, there is a 3-month guaranteed lifetime. And then when it reaches EOL, we will not be able to provide any guarantee about the output and hence the capture of that. So it's worthwhile considering replacing between these two. That's an important aspect. That's about considering when to change the pacemaker battery or pacemaker itself, and then a little bit about the life of the battery. And the life of the battery is dependent on the battery capacity. Battery capacity is represented as ampere hour. So in this case, we have sketched the 2 ampere hour battery. So what do we mean by that? When I implant, or let's say I draw 1 ampere of current from this battery will last for 2 hours. So So if it is a 1 ampere hour battery, if I draw 1 ampere of current continuously for 1 hour, then this battery will last for 1 hour. But then the pace, so long we discussed about the current outgo, and as the result of that energy outgo for the pulse that we are delivering. But that's not the only current drain that we're talking about. In a pacing system, there is energy consumption when the pacemaker senses there is energy consumption, and then there is a microprocessor that is running. You need power to run that. And then there is a capacitor network to drive the output that also consumes some power. And the modern pacemakers are monitoring itself and it stores the electrograms, etc. That also consumes power. So there is a certain amount of baseline current consumption and also additional current consumption because of these additional activities by running the algorithms, etc. So we will not be able to calculate what is the continuous current outgo. The pacing output current drain is one of the aspects of this. So in this case, if we can calculate the continuous current outgo for this 2 ampere hour battery, in this case, let's say 25 microamperes. So in the current pacemakers, typically the ampere hour is about 1.2 to 1.5 ampere hour. And then the current outgo is not 25 microamperes, it's about of the order of 15 microampere hour. Let's say 1.5 ampere hour battery, 15 microampere current drain, continuous current drain. Then when you divide the ampere hour by the continuous current drain, we know how many hours the battery would last. Then we can estimate the longevity in terms of months or years. But it's difficult for us to calculate. The programmer actually is able to measure what is the continuous current drain based on the history of the pacing and sensing that happens. And it applies that and tells us how much the battery is going to last from the time when we are interrogating. So that's the way it is calculated. So we don't have to calculate that. So it's good to go by the programmer suggestion when we interrogate. And then that's, again, it's not absolute. So there is likely to be a little bit of variation. So we need to keep that in mind as well. And lithium iodine battery is a reasonably good battery. It does not undergo a sudden premature failure, and that's why lithium iodine battery is used today. And in the most recent pacemakers, what is used is actually a battery that is used in ICD. It's lithium silver vanadium oxide, also with an additional compound called carbon monofluoride that makes the battery last a little longer. And typically that is used in an ICD because you need a high power to be, or high current to be suddenly drained when the device needs to deliver a shock. So ideally, so in the conventional pacemakers, it's a lithium iodine battery which meets all our criteria, and it should have a very slow discharge rate, and it should not, expel any gas or liquid from the chemical reaction, so that the battery does not get corroded inside the patient chest, which we all are familiar with the conventional, batteries that we use in our electrical appliances, which does not happen with a lithium iodine battery. Okay, so we touched upon this already when we are talking about programming the output to enhance or optimize the pacemaker longevity. Keep in mind when we are programming the output or doubling the output, the energy outgo, because it varies by the square of the voltage. But when the impedance increases 2 times, then the energy outgo is halved, so that you can say that energy outgo becomes half of that. The battery would last significantly longer, but not exactly double, because there is other current drain that happens from the pacemaker, as I described a little while ago. So yeah, while you're programming the output, another thing that you may want to consider is also program the output at around the battery voltage. Let's say I want to deliver 4 volts output from this battery. Then I cannot directly deliver 4 volts from a 2.8 or 2.5 volt battery. So this need to charge a capacitor network, and that will deliver together 4 volts. So now I need to drive that capacitor network, and there is some residual energy left or wasted in the capacitor network. So that might make the energy outgo actually more than what would actually, when you calculate the 4 volt, would actually entail. So it's a good idea to consider programming the output at around battery voltage. That's why a 2.5 volts output between 2.5 and 3 volt is an optimal one, which is very much possible usually when a pacemaker thresholds are around 1 or 1.5. Okay, so that's about pacemaker polarity and stimulation aspects. I've already spent about, just about half an hour. Yeah, we started at 7:30. It's 8:10. So is there any question before I go into the sensing? I would request Dr. Manish to comment on some clinical relevance of this before we go into sensing, or we'll take some questions before we get into that.
Yeah, if you have any questions from this one, the students, anyone has got any questions or concerns? Have you all understood anything, everything? So I think Mr. Govind has spoken in detail regarding battery life and how it works and the importance of programming the right output and the pulse width to restore battery and all that. So if you have any questions, we'll take it, or else we'll proceed with the next section.
Can we know what is the composition of ICD battery again, sir?
Okay, so it is made of lithium, silver, vanadium oxide, and an additional compound called carbon monofluoride. The most recent ICDs have that. So that has a higher, that enables us to draw a large amount of current quickly from the battery. So they are high rate batteries, and these are more suitable for ICDs. But increasingly now all companies have started using a similar battery for pacemakers also. If you're looking at the most recent top of the line pacemakers that come from all companies, we increasingly use the lithium, silver, vanadium oxide, carbon monofluoride based batteries.
Yeah. This one, Mr. Govind, this one, I think recently I had a lecture for them on troubleshooting pacemaker ECGs, wherein I touched upon a little bit of sensing, capture, and all those things, over sensing, under sensing, and all that. So they may be, this one, this one, they must have understood those things. So, this one, we can go through it quickly. And then on the pacing cycles, I think, they haven't understood pacing cycles, timing cycles. So, we'll concentrate more on that. I think this part, the over sensing, under sensing, and capture, I think not the first part what you did, but the second part, about sensing, if those things, I think I addressed the other day. So, but we can quickly go through if they have any concerns or something, okay? And then we'll go on to this one, pacing cycles, okay?
Right, sure. I will, sir,
sir, what is the relevance of this chronaxy and strength rotation curves? Clinical relevance?
No, you can go ahead.
Right. The point, when I was describing the chronaxy point, I'm sure you could gather that, that's the point of combination of amplitude and pulse width where the energy outgo is the least. So when a patient, after implantation and also when the patient comes for a follow-up, we check the output, we check the voltage threshold, and you want to build a bit of a safety margin. So that means usually it's a twofold safety margin. Let's say if your voltage threshold is 1 volt, then you ideally want to program an output of 2 volts. And so that even if there is a change in the thresholds, there is a reasonable safety margin that is already built in our output. But then while you're programming, that reference point should ideally be the reference point which refers to the least energy outgo. You could check the threshold at 0.6 when everything is good. The threshold will be, you check the threshold at 0.4, let us say, you get a voltage threshold of 1 volt. For the same case, you make the pulse width 0.6 milliseconds and check the threshold. It will be less than 1 volt. Let's say it becomes 0.7 volts. Then I may program an output at based on 0.7 volt, but that's not the real chronaxy point. Then we need to actually find out. So it's good to have, if the time permits, we should ideally get that chronaxy point, which is the least energy outgo point of a combination of amplitude and pulse width, and program an output based on that, which is not possible in a practical setting. So that is why we can generally think of the nominal setting, which is 0.4 or 0.5 millisecond pulse width. And usually a threshold is under 1 volt, and double the output, which is double the voltage of the threshold as an output, which is good enough. But the point comes when there is a patient where you encounter where the patient has a higher threshold. That's where it is worthwhile considering both of this and try to reach this point and then program an output so that you can conserve the battery as much as possible. Dr. Manish, you want to
yeah, it's the same thing, I mean, the idea about chronaxy and Riobase is to find out make sure that you conserve as much battery as possible. You use minimum amount of output for each pulse that you deliver. At the same time, don't compromise on safety. So generally, like what Mr. Govind said was, we although we get a threshold of 0.7, 0.8, you never see a pacemaker being programmed at 0.7, 0.8 because there might be slight variation in threshold. And in a dependent patient, if it doesn't pace, then you might have a syncope on the pacemaker. So what the norm is to find out the threshold during each programming and then program the output at twice the threshold. So that's kind of a chronaxy. That twice is the margin. So safety margin to make sure that even if the threshold varies a little bit, it doesn't matter, and patient safety is not compromised. On the same time, when you're increasing the output and increasing the pacing output to twice the threshold, there is a risk that you will drain the battery a lot. So if you can, if needed, most of the time it doesn't make a difference, but you can adjust the pulse width and see what is the basic the pulse width, minimum pulse width at which you get good threshold, and you can double that. So but as Govind said that in most often at a pulse width at 0.4, 0.5, it really doesn't make a difference. Yeah, so routinely we just keep the pulse width at 0.4, 0.5 and just see the threshold and double the, keep the output at twice the threshold. Okay, that's the only relevance. Yes.
Sir, so for instance, if a pacemaker has a threshold of 1, so normally we'll keep the output double of that, let's say 2 volts. So that would be the chronaxy point.
No, that's not the chronaxy point. That is not the chronaxy. Chronaxy point is if you have to go in real detail to find out, first find out the threshold at infinite pulse width. That is maximum pulse width is 2 milliseconds. What is the threshold? Then you find the threshold at around 0.6. Assume at 2 pulse width. Then you double that and see at 1.2, and if you reduce reduce the pulse width, at what point it loses capture, and that point becomes the chronaxy point. So, but that is only if you want to really find out. But for clinical relevance, it's that really doesn't count so much. What is more relevant is to make sure that safety margin is not compromised. That's why you program the output at twice the threshold. And pulse width, we generally do not compromise. Do not interfere much or vary much unless the thresholds are very, very high. Only if the thresholds are very high, then adjusting the pulse width would make a difference, because otherwise you'll drain the battery early. Okay.
Okay, sir. And Riobase, sir, it will be kind of it will be threshold at max again.
Riobase is more of a theoretical concept. Imagine an infinite pulse width, and then if you were to stimulate it, at what point you will find a loss of capture. That is Riobase. Okay, so but in a pacemaker you can't have an infinite pulse width. In a program pacemaker, the maximum pulse width is 2 milliseconds. So at that, for practical consideration, your Riobase would be at 2 milliseconds. How much is the threshold? Okay.
Okay, sir. Okay, yes.
Yeah, so the important point you want to remember is, let's say, you check the threshold at 1.5 milliseconds. It happens to be, let's say, 0.5 volts. And if you increase the pulse width to 2 milliseconds, it's not going to reduce it further below 0.5 volts. It might at best go to 0.4. That's it, not beyond that. So you're not gaining any pacing efficiency, but the energy outgo is significantly higher. So, yeah, that's what it is.
Yeah, sir. So, and chronaxy is basically double of Riobase. That's what, sir?
No, double of Riobase voltage. And then at that constant voltage, you are determining the pulse width threshold.
Oh, okay.
You're keeping that output constant in voltage, and you're determining the pulse width threshold. So that combination is the chronaxy point.
Sir, the energy derived to the myocardium, the formula is there, no, sir? And in that formula, if the resistance is increasing, the energy should decrease, sir. Previous
Yes,
slide.
yes. When you go to when your in a resistance increases, then the energy outgo reduces because the current drain reduces because of Ohm's law. Right here.
But if resistance increases, so we need more energy to stimulate, no, sir.
Yeah, so that's right, but that's up to a limit, right? So that means if the resistance increases, so that is why I said, it's not just one aspect of the resistance. I did not go into the detail of that because of the time restrictions. So, the impedance has several components. One is the resistance experienced by the flow of current across the conductor wire, which actually by design is the least resistance. Unless there is a fracture, usually it's about 50 ohms or something. It's a very low resistance. But then when it comes to the tip is in interface with the myocardium, there is a little bit of a resistance. So that's the real resistance that may impede the flow of electron into the myocardium. So that can adversely affect the flow of electrons. But there is another resistance which is called as a polarization resistance. So this is made more. That is when, in polarization, what happens is, imagine you are pushing electrons through the wire to the lead tip, which is a negatively charged particle, which attracts a lot of positive ions at the lead tip. Now, as the positive ions accumulate at the lead tip, as you are delivering the output, it is surrounding the lead tip. Now, if you want to make more electrons flow out of the tip, ideally you want to increase the surface area of the electrode, the tip electrode, so that the accumulation has some gap so that electrons can go out. But if you increase it too much, then your pacing efficiency is not good. So ideal electrode is the one that has a very small diameter but a larger surface area. And so this is made as a porous one. So this is what actually makes the difference. So in this case, although this is expected to reduce the current outgo from there, it makes the pacing efficiency better. So you are getting a better threshold at this point of time, right? So, and that is why we are talking about a limit. So if all things being equal, if let's say 1 month before you implanted a pacemaker, you are delivering, you check the threshold, it's 1 volt, and then the impedance on the conductor wire is very, very little, so the electrons are reaching the lead tip, then the polarization impedance is relatively higher, let's say 1500 ohms, then it becomes more efficient and it's able to give you a lower threshold. Although at that tip, the current outgo is relatively lesser, so the current drain is lesser from the battery because your output, your threshold is lower at that point because it is more efficient. But imagine at the same time, the polarization impedance becomes, very low. That means it allows a lot of current to go. Then that's not efficient. And that is why it's a relative factor. When you're looking at directly the relationship of this, yes, the current outgo is lesser. So you expect you need more energy to capture. But here, because of that polarization impedance there, it is going to make it more efficient. As a result of that, your threshold is lower. So you can program a lower output, and as a result of that, your battery drain is lesser. So it's a more relative concept that you're talking about here. I hope that was
impedance is maximum at lead and myocardium junction, sir.
No, lead conductor impedance is low, very low. It's made by the manufacturer.
Yeah. Where it will be maximum, sir?
So it is at the lead tip interface. It will be higher. So we want that impedance to be slightly higher. So that what makes the lead impedance a little higher.
Okay, sir.
So what we are talking about is a combination of both. When we actually do the practical measurements, it's a combination of both. So that means the conductor impedance is lower. The impedance that is relatively higher is the interface, the polarization impedance. That's what we are getting. So when that is higher, it becomes more efficient. So you get a lower threshold and it allows you to program a lower output.
So polarization impedance is the one at the tip. Is it the same or different? Sir?
Yeah, so it happens at the tip. That impedance is because the electrons come to the lead tip, and that is surrounded by the positive ions.
So when you measure an impedance, it is impedance across the system. It includes everything. So lead, tissue, and polarization, everything. You don't get individually. But by and large, what Mr. Govind is trying to say is the lead impedance per se, because of impedance by current flow across the lead is less. So it should be contributed by the tissue or by the polarization artifact. But you can't get individual values clearly. So what we measure is when we measure impedance, it is across the system, from the battery till the tissue. It could be anywhere. So based on if it is too high, then you have to deduce it. Whether the lead wire is a problem, whether there's a conductor fracture across it, or whether there's a tissue impedance being very high or something else. Okay.
Yeah. So the other point is there is a patient that has a good impedance, good threshold for a long time. Suddenly he comes with a high impedance, and in this case, the lead has fixated and there is no chance of interface and polarization impedance to change. The only thing that could have changed would be the conductor fracture. And when that happens, the impedance is not just about 2000 or so. It is usually 5000 upwards of that. So in which case there is a total severance of the electrode, and then there is no current is flowing. And yes, so at that time there's nothing delivered at the lead tip, so there is a loss of capture. I guess that reasonably explains. Can I go ahead?
Yeah, sure.
Okay, right. So, okay, the sensing part, yes, quite a bit of it is described already. Then I can, shorten this. Yeah, so what the pacemaker measures is actually the intracardiac electrogram, the amplitude of the intracardiac electrogram between two electrodes, if it is the bipolar one. And then if it is unipolar, yes, if it's a true unipolar electrogram amplitude is what measured. There's one other aspect that is also relevant looking at the sensing aspect is that there's a slew rate, which actually represents the rate of change of voltage. How fast from the peak to the nadir the voltage changes with respect to time. So you all are definitely familiar with the dP by dt dealing with echocardiography. A similar thing you can apply. It's dV by dt. This represents how fast the voltage is changing, how frequently the voltage is changing. If it is higher, then the frequency is higher. But let's say in a T wave, it is changing slowly, so the frequency is lower. So the slew rate is related to the frequency of the waveform. Higher slew rate relates to the higher frequency, lower slew rate refers to the lower frequency. So pacemaker electronics have a filter. We want to filter out all the unwanted waveforms. Typically, we want to filter out myopotential if it exists. We want to filter out the T wave also. The T wave has a lower frequency. Myopotential typically have a higher frequency. So there is a band pass filter. So this will allow a certain frequency of the waveform, which is typically of the waveform with respect to the R wave and P wave. So that is what it will allow to go through. And that filtering is based on the frequency characteristic of the waveform. That is related to the slew rate. So when the slew rate is higher, the frequency is higher. When the slew rate is lower, the frequency is lower. So at there is no programmable parameter relevant to that. But then at the time of implantation, it is worthwhile noting that value. Typically, when you get a good R wave, the slew rate is also higher. For an R wave, the good slew rate is, it should be 0.75 volts per second. How frequently it's changing, that's what it is. So for a P wave, it should be more than 0.5 volts per second. In case you get a reasonably good R wave, and then let's say only about 0.4 volts per second as a slew rate, you may want to reposition it at that time. because there is no other opportunity. The pacemaker, once it's connected, there is no way that you can alter that. But when you get a good R wave, you will also get a good slew rate, and it becomes more important when you are actually implanting an ICD, where it has to accurately detect the low slew rate, low amplitude R waves. So then it becomes important. So at the time of implantation, it's worthwhile looking at it. You will get a good slew rate with a good R wave. In the event of a low slew rate, you may want to reposition the lead to another position to get a reasonably good slew rate. And then you need to pay attention particularly, sometimes when you're implanting, most of the time you get a good R wave. Sometimes, because some pathological reasons, you get a smaller R wave no matter how much you explore. So let's say you get up only 3 to 4 millivolts R wave. Note the slew rate. The slew rate should be reasonably good at that point of time. So that's the rate of change of voltage in the R wave. And then yes, as I said, the electronics filters it and amply enhances this, and then that is put through the sense detector. That's where we program the sensitivity setting. Typically, you want to have in the ventricle an amplitude of 5 millivolt or more R wave and 1.5 millivolts or more of the P wave. And at follow-up, even 3 millivolts in the ventricle is acceptable value. And you program a sensitivity setting. I'm sure you're familiar with that. The lower the value, higher the sensitivity. Lower sensitivity might, expose the patient for oversensing, and you want an optimal sensing. And when you program a higher number, you're making the sensitivity low, then the pacemaker may not sense adequately. An example of a under sensing, where the R wave is not sensed and it ends up pacing, and it might end up pacing on the T wave, which could be dangerous in a patient that's vulnerable for getting ventricular tachyarrhythmia. And the opposite is also true, which is the oversensing. It's oversensing something when there is no waveform corresponding to that. This might represent an electromagnetic interference. This might also represent a lead-related problem. When there is a lead fracture or an insulation break, there could be an oversensing that can happen, that can reset the pacing cycle. So we will see that in greater detail. Both insulation break and a wire fracture can affect the sensing characteristic adversely, and your polarity, whether the setting is unipolar or bipolar in configuration, can also affect the sensitivity. Electromagnetic interference, the conventional electricity that we deal with has a 50-60 hertz, which is the same as the peak hertz of the R wave frequency as well. So we cannot filter it out adequately so that it will interfere with the pacemaker if the patient comes into contact with that. So polarity, when we said, yes, it can interfere with sensing, because unipolar system senses between the tip and the can. So this can pick up the myopotential and get oversensed. And if there is an electromagnetic interference, there is a large antenna by the body tissues. It can easily pick up the electromagnetic interference, even if it is a little far away. So unipolar pacing system inherently are more susceptible for oversensing, unlike a bipolar, where the entire sensing is between the tip and the ring electrode, which is less susceptible for oversensing. So that's one aspect. The insulation break and also the conductor fracture can cause oversensing and undersensing. So if you're looking at a bipolar, there can be two forms of insulation break. There can be an outer insulation break, there can be an inner insulation break. If there is an outer insulation break, then the R wave amplitude that's coming into the pacing system through this conductor wires can get seeped out of this, and the amplitude that is seen by the pacemaker might become lesser. So then that might cause an undersensing. Let's say there is a fracture or inner insulation erosion that might happen. This might result in a contact of the anode and the cathode that can cause a short circuiting, as well as it can also generate an electrical impulse like a make-break signal that might result in an oversensing. So both of this can cause oversensing and undersensing. So also an electrode fracture, like in this case, there are several strands. let's say there is a fracture in two of these strands, but the others are in contact. So the pacing lead is also moving with the heart. So these two electrodes, the severed strands, will touch each other, rub on each other. That will cause a make-break signals that can come, and that will be seen by the pacemaker as an amplitude that happens, small amplitude, and that would cause oversensing, and that might reset the pacing clock. As a result of that, when there is no R wave, the pacemaker will oversense, and that might reset the pacing cycle, and the patient may come up with loss of pacing in this case. Of course, if there is a serious enough fracture, as we said, by application of the Ohm's law, the pacing stimulus that is delivered at the tip will become significantly smaller, and that will be lower than the threshold, and that might not capture. So both oversensing and a loss of capture can happen when there is a fracture. Of course, there will be an impedance change. You will detect it based on that. So both wire fracture and the insulation breaks can cause oversensing as well as undersensing. So that is one. Just to give you some of the examples of oversensing. This is actually an electrogram from an ICD. This is a dual chamber ICD. The top is the atrial electrogram, and this one is the ventricular electrogram. This patient probably had a lead fracture. You can clearly see the nice R wave here that I'm pointing here. In between that, you find an artifact because the electrode have fractured, and these are the make-break signals that you're seeing, which is very typical of the make-break signal when there is a lead fracture. Of course, the impedance will be higher, and you can corroborate that with this noise. So this is what, when you find a more than 30% change in the impedance, sudden change when the patient has been coming regularly for a follow-up. This time you found a 30% increase in the impedance, then we want to suspect a lead fracture, at least one of those strands. Then make the patient make the arm and the shoulder move significantly to try to elicit the make-break signal. And if it generates this kind of a noise, then it definitely is starting a fracture, and you may want to plan the change. Or oversensing happen. So that's what you want to look for when the patient comes with a significant increase in the impedance. Similarly, if there is a lower impedance, it indicates insulation erosion. So that might also either, in some cases, pick up a myopotential if there's an insulation break in the coil of the extra wire that is there in the pocket. So that might pick up the myopotential sometimes. Or, as we said, not adequate R wave can reach the pacemaker, and it may undersense as well. So an oversensing and undersensing can happen. And this is an example of a T wave oversensing that you can see here. This is the ventricular sense happening, and this is another ventricular sensing on the T wave. You will not see that in a conventional pacemaker. Even if it happens, it will fall in the refractory. We will see that in good detail in the timing cycle that we're going to take up. And here's an example of undersensing that's happening. As a result of that, there is pacing, and this is a functional loss of capture, because when the stimulus is happening outside this myocardial refractory period, it's capturing. So this is a functional loss of capture because of an undersensing. So in this case, you may want to increase the sensitivity of the pacemaker. In the previous one, yes, in the make-break thing, there's no point in reducing sensitivity because it's ultimately the lead fracture that's causing. But in this one, you might reduce the sensitivity, meaning increase the sensitivity setting number, which might avoid the T wave oversensing. So in this one, there is undersensing. You want to increase sensitivity, so it will correct the setting. And this is a typical example of electromagnetic interference. So here again, ICD. This is the near field electrogram, tip to ring electrogram. This is a tip to coil electrogram. It's like a far field, from the can to the RV coil. So this is like a unipolar electrogram, which is likely to pick up more electromagnetic interference. You can see that is reflecting in the near field as well. That is being oversensed by the device. So if this patient was a pacemaker dependent patient, because continuous oversensing, the pacemaker would not pace, so which is the possibility. So that's in this case, there's nothing that you can do by the settings of the pacemaker. We should help the patient identify the source of electromagnetic interference and avoid that if it is from home or office related one. But this might happen in the hospital, where your surgeon is likely to operate in an pacemaker implanted patient with an electrocautery, and that's why we typically program the pacemaker to a VOO mode. Yeah, or you recommend the surgeon to use a bipolar cautery when operation is significantly away from the pacemaker system itself. That's the electromagnetic interference. And then this is an example of a myopotential oversensing, which is picked up from the Ellen Rowland book, which is very typical of a unipolar system. You don't see that in a bipolar system because CAN is not acting as an electrode. So typically this myopotential comes from the pectoral muscle in a unipolar system. You can recognize the difference between electromagnetic interference and then the myopotential. Very, very rarely in a bipolar system, which is where it picks up the diaphragmatic myopotential, which is extremely rare, which can be managed by reducing sensitivity. Again, when a unipolar paced patient comes for a follow-up, always make the patient to activate the pectoral muscle by moving the shoulder, by doing a namaste kind of posture with pressing the palms together, and to look for myopotential happening to rule out that, particularly when the patient threshold is good, but the patient is reporting symptomatic. It's possible that it's myopotential oversensing. You want to do that and rule out the myopotential, particularly if it's a unipolar system. So that's about the sensing and the sensing related problems. So then we get into the timing cycle. As Dr. Manish said, we want to spend more time on the timing cycle. Typically, the single chamber is much more easier. So I will not pause at this point. So let me straight away get into this. We'll take the question at the end. So in a single chamber timing, you have a lower rate and corresponding to that a lower rate interval, and you program a refractory period and a blanking period. We'll see why it is there. And if it is a rate response pacemaker, you also program a upper sensor rate. We will talk about that. And then there is something called hysteresis, we'll talk about it. In a single chamber ventricular pacemaker, the lower rate, in this case, we program 60 beats per minute, which corresponds to a RR pacing interval of 1000 milliseconds. The pacemaker delivers the V pace, starts the clock of 1000 milliseconds and delivers the next V pace. And it starts the clock all over again and starts to run it. Along the way, it finds one ventricular intrinsic event happening, which is sensed by the pacemaker, and it calls it as a V sense. V pace is called as a VP. And then here it resets the clock back to 0 and starts the lower rate interval and then delivers a V pace here. So my lower rate interval is V pace to V pace or V sense to V pace. So this is happening inside the heart. This is not in our control. So this is not the lower rate interval. So it's V pace to V pace or V sense to V pace. If you have implanted a single chamber atrial system, it will be A pace to A pace, and then A sense to A pace in an atrial alone pacemaker or a AAI pacemaker. Okay, so then we are stimulating and sensing, and in order to accurately sense, we program a sensitivity setting. Typically, it's about 2.5 millivolts in a ventricular pacing setting. So in Medtronic, it is 2.8 millivolts. And if you don't do any other thing and only rely on the sensitivity setting, then any amplitude of the waveform that happens inside the heart, which is bigger than 2.5 millivolt sensing, the pacemaker is likely to sense, which means it can sense the pacing stimulus itself, because pacing stimulus is 2.5 volts, which is 1000 times more powerful than 2.5 millivolts. So it is likely to sense that, and it might even damage the pacing circuitry, because my pacing sensing circuitry is designed to handle millivolt magnitude, waveforms. it can sense the evoked R wave that comes from the pacing stimulus, which is typically very large, which it can sense if I don't make any restriction for that. Similarly, it can also sense the T wave if the amplitude of that is big. We don't want to sense any of these. But yes, I want to sense the R wave if it is an intrinsic R wave. And I reset my clock based on this. So we are interested in sensing only this. We don't want to sense any of that. But if we rely only on the sensitivity setting, the pacemaker can sense all these waveforms. So we want to put some restriction, and that's where the refractory period and the blanking period comes into play. On delivering a V pace, there is a programmable interval, which is a refractory period. So during which time the pacemaker can sense the later part of that, then it will ignore that sensing. So the duration of time after a paced event or a sensed event, we don't want to sense the same QRS one more time or the T wave. And in order to avoid or ignore that sensing, then we have the refractory period. Usually it's a programmable period, which is typically about 300 millisecond in a ventricular single chamber pacemaker. And if there is a sensing that's happening, the pacemaker will call it as a refractory ventricular sense, and it will ignore it and it will not reset the clock, like in this case. So it would have started a refractory period on the first V pace also. It is not put on the scheme here. So here on the V pace, it started a refractory period. Here, actually a ventricular PVC is happening. And that happens to fall in the programmed refractory period. Even though it's falling inside, it falls in the refractory period, even though it's a true ventricular event. Here, because it's falling in the refractory period, it's not going to reset the lower rate clock. But had it happened outside, it would reset the lower rate clock. But another point that you would want to remember is, if there is a refractory ventricular sense just like this, it would start one more refractory, even though it did not reset the lower rate clock. Right? By this time, the lower rate clock timed out and delivered a V pace here. So that's the little disadvantage of a longer refractory period. If you program a longer refractory period, and then if this QRS falls or the PVC falls a little later, and if this T wave happens here, it might pace on the T wave. So that's why you don't program a very long refractory period. Yes, so this is the behavior of the refractory period. And that's not all. And when we deliver a pacing pulse, we talked about polarization, which means we are delivering electrons. There's an accumulation of electron, which is of a good amplitude at that point of time. And after we stop the pacing pulse at the end of the pacing pulse duration, this slowly dissipates. Though this time is a highly powerful, noisy time at voltage amplitudes. But as we said, the pacemaker designed to sensing circuitry is designed to have millivolt amplitude. We don't want the pacemaker sensing circuitry to get damaged. So that's why the initial portion after the pacing event inside the refractory period is a blanking period where the pacemaker senses nothing. So that's a totally blank period. It does not even sense that. Then after that, it's the refractory period where the pacemaker will sense it, but it will call it as a refractory sense. It will not reset the clock if there is a sensing here. And in the current pacemakers, the blanking period, the same chamber, the ventricle, it's not programmable. It's an automatically adjusting one. It will automatically vary between 50 and 100 milliseconds, and you could program the refractory period something like 300 millisecond, and in a typical dual chamber pacemaker, it's about 250 millisecond. So the first portion is totally blanked, and then the next portion is the refractory one, where it will sense and it will not reset the clock. In other words, it will ignore that event. And the same thing will happen after a sensed event also. The question is, why do we want that blanking in a sensed event? So there is an R wave that's happening, changing frequently at a high frequency. We don't want to sense all over again. There is no fear of the sensing circuitry getting damaged, but we don't want to continuously sense that noise that's happening. And that's why it's blanked after a sensing event as well. So on a paced event or a sensed event, it starts a refractory period, which is a programmable one. And the first portion of that is the blanking period, during which the pacemaker does not sense anything. But during the refractory period, the pacemaker might sense. Typically, it may be a T wave or a PVC that will be ignored by the pacemaker, and then it would start one more refractory period. That's the blanking and the refractory period. And if you are implanting a rate response pacemaker, then the concept of the sensor indicated rate comes in. The time is, yeah, we still have about 10 minutes time. Sensor indicated rate. So there is, you program a lower rate, and you don't want to pace the heart at a very fast rate in the, when the patient is physically active. So you want to put a limit to that. That's what your upper sensor rate or the upper activity rate. And the pacemaker will pace the heart at a rate between this at all times, depending on what the patient's level of activity is. If he is totally at rest, it will be pacing at the lower rate. When the patient is maximally active, it will not pace faster than the upper tracking rate. At all other times, it is in between that, which is the sensor indicated rate. You can, so I'm not going to the detail of this at point of time. There is an accelerometer sensor that is there in the pacemaker, which vibrates when the patient is moving in the anterior-posterior direction. This is kind of hung with a fulcrum on the pacemaker circuitry. So so you can imagine this is the skin on the chest, and then it is vertical on the patient's chest. When the patient is moving in the anterior-posterior direction, this is going to vibrate. It generates some electrical potential. Don't confuse this with the sensitivity or the pacing potential. This is a small potential that comes from the piezoelectric crystal that is proportional to the activity that patient is doing, which by means of an algorithm is converted into the level of activity and corresponding to the rate at which we want to pace. And so we program a lower rate, in this case 60 beats per minute, and the upper sensor rate of 120 beats per minute. And the pacing rate would be anything between that, which is determined by the sensor that I showed previously, and it will be anywhere between the lower rate and the upper sensor rate. So the way to deal with or easily deal with the upper sensor rate is to consider the sensor indicated rate to be the lower rate provided by the pacemaker at this instant for that patient. Let us say this patient, my lower rate is 60, upper sensor rate is 120 beats per minute. Now this patient is doing a gentle walk. Now the sensor says pace at a rate of 80 beats per minute, let us say. So now 80 beats per minute at this instant can be thought of as a lower rate provided by the pacemaker, so that your timing cycle will fall into place. The patient goes to sleep, then the sensor is not vibrating, it will pace at the lower rate here. So this is the lower rate at this point. Now this patient is running. Now the sensor is vibrating maximally. Then here you have put a limit. So the timing interval will be 500 milliseconds. So at this point, the lower rate, the interval is the 500 milliseconds. So it varies between that. So it is for the ventricle. Similarly, if you implant, and of course, when you deliver a pace, whether it's sensor indicated rate or whenever you deliver a pace, then it starts the refractory period and the blanking period. And the reason why it is there is it's for the same reason. And of course, if there is a ventricular intrinsic sensing that's happening right after this, it's going to reset a clock. And if it is the upper sensor rate, then the clock running at that time will be 500 milliseconds according to this programming. So then I'm sure all of you are familiar with the VOO mode, where it's completely kind of blank. You go on pacing, ignoring whatever happens inside the heart automatically. So here, this is ignored, and this is what you want to program when your patient has to undergo a surgery where the surgeon is likely to use a unipolar cautery, and it is safer. And of course, I'm sure you also know that by placing a magnet on the pacemaker will stop sensing and it will go into a VOO mode at a slightly elevated rate. Each company has a different, magnet rate, by which we also can recognize what company pacemaker it is, and also to a greater extent about the battery status. When the battery reaches ERI, when the magnet is kept, it will not pace at the magnet rate of, let us say, a higher rate. For Medtronic, it is 85. When it reaches ERI, the magnet rate will drop to 65 beats per minute. Both of these are not programmable rates. And in a VVI, as we said, in this case, if you're programming a rate of 60 beats per minute, we're delivering a pacing pulse here, starting a refractory and the blanking that we have programmed, and the clock is running for 1000 milliseconds. It saw intrinsic ventricular sinus event happening. So this is called as a resense by the pacemaker, well outside the refractory, resets the clock. It also starts a refractory and the blanking, and at the end of the lower rate interval, it delivers a V pace, doing one more refractory, starting one more refractory and the blanking, it would start another lower rate interval here. So that's how the VVI or the AAI runs. And if there's an electromagnetic interference that happens, periodically like this, yes, in this case, it delivered a V pace, it started a refractory, and the lower rate time also started. But before the expiry of the refractory, there was a noise, electromagnetic interference, and it's restarted one more refractory. And there is another pulse of an electrical impulse that came, that is from outside the heart, and it is also in the refractory. It started one more refractory, so it ignored both of this. The pacemaker never had an opportunity to reset the clock, so it actually delivered a V pace. This is what is called as a noise reversion. Actually, in presence of continuous noise, the pacemaker would start pacing because of this kind of noise recycling that happens. But we still want to program to a VOO mode during surgery because the cautery impulses are quite powerful that might damage the pacing circuitry as well. That's one more reason, in addition to inhibiting the pacing at some point of time for the patient. So it would be a good idea to ask the surgeon to do short bursts in case you don't have a magnet, and then in case you're not able to program it to a VOO mode. And another option is to use a bipolar cautery. And so long as the bipolar cautery is more than 15 centimeter or half a foot away from the pacing system, then it would usually not interfere. But if it is a unipolar system, then below navel, you can go ahead and do that. If any surgery has to be done above the navel area, you have to use either a magnet or program it to a unipolar or a VOO mode, and then keep the neutral paddle in the gluteal region, not on the back of the patient. And then yes, here is a T-wave over sensing that is happening, and in this patient, the QT interval seems to be slightly longer, and it is happening outside the refractory period. So here it is sensed as ventricular sense, and it is actually causing a resetting of the clock and ends up pacing in the ventricle at this point. So your effective pacing rate is lower than the lower rate, because this time is actual effective time is longer than what we intended to do, which is this, maybe 60. But whereas if your the QT interval happened to be 300 millisecond, and if this lower rate interval is 1000 millisecond, then effectively we are pacing at an interval of 1300 millisecond, which would be something like 45 beats per minute. Your patient could be symptomatic. So in this case, if you do not have a programmer on hand to identify it's a T-wave over sensing, and if you're sitting in the OPD and you only have the ECG, then look at where it delivered a V pace and work your time backwards if you know the lower rate, and if it ends exactly on the T-wave beat after beat without even a programmer, you know that it is a T-wave over sensing. So there are two ways that you can overcome this. You can reduce sensitivity, provided your R wave is good enough to allow you to do that. If not, you can increase the refractory period. That also has a little bit of a problem. If you program a high pacing rate, lower rate, then if you increase the refractory period, then competitive pacing can happen. So these are the two ways you can manage that. But in a single chamber ventricular system, or even a dual chamber conventional pacing system, encountering a T-wave over sensing is extremely rare, although it happens in an ICD, because that does not have this kind of a refractory period. So we'll deal with that later. So this is a T-wave oversensing that rarely happens in a pacemaker. You can deal with either by reducing sensitivity or by increasing the refractory period. We talked about the rate response pacing. You program a lower rate and an upper sensor rate, and then there is a corresponding refractory period as well. And another important aspect that you want to consider in a single chamber system is what is called as the hysteresis rate. So you have given a pacemaker for a patient who has an intermittent bradycardia, and you had to end up giving a ventricular pacemaker because patient could not afford a more comprehensive dual chamber pacemaker. So when you want to pace for some physiological reason at a slightly decent lower rate. But when the patient has an intrinsic rhythm, it's okay to allow that intrinsic rate to be at a lower rate than the lower rate. Then we can program the hysteresis function on. So when we function on, we program two settings. One is the lower rate, which is in this case 60 beats per minute. And we also program a hysteresis rate, in this case 50 beats per minute. When we program this on, every time the pacemaker paces, it starts a lower rate interval and paces at the end of the lower rate interval. Now it started a clock again. As the lower rate is running, it saw V sense, and on V sense, when hysteresis is on, it does not start a lower rate interval, but it starts a hysteresis rate interval, which in this case is longer, which is 1200 milliseconds. So here it waits for 1200 milliseconds. So if there is no intrinsic event comes for 1200 millisecond, it's delivered a V pace and it will start a lower rate interval here. But imagine now at 1100 millisecond, there is a V sense here. Now it will restart a hysteresis interval. So which means effectively you are allowing a rate below the lower rate, which happens to be 55 for this patient. It will continuously allow that. But when the rate drops to as low as 50, it will do one pacing, and from that time onwards, it will pace at a rate of 60 beats per minute. So for that to happen, there should at least be one event faster than the lower rate for hysteresis to kick in. So this will be useful for a patient that has intermittent bradycardia, where you want to not pace more often, but when you want to pace at a slightly higher rate. And it is not uncommon in our country where patient with sinus node dysfunction with a good AV conduction because of economics reason and also a future risk of patient developing an AV block, you end up putting a VVI pacemaker. For them, you can make use of this. You are reducing pacing, and that also contributes to slightly enhanced longevity of the pacemaker. So this covers the single chamber timing. So when we are talking next on Sunday, we will go into deeper details of the dual chamber timings only, which we will discuss in greater detail. So I stop at this point and take your questions on any of these aspects, including the timing cycles. And yes, I would request Dr. Manish also to make comments on the timing cycles.
Sorry, the last part. I was in a call with someone else, with a patient. Anyways, this one, you know, do we have any questions from the students? I think it was a one. Yeah, tell me.
Yeah, Rajesh.
Actually, sir, what is the usual blanking period and refractory period you will set, sir? Is anything like that fixed, or it will be changed for every patient, sir?
No,
actually,
actually,
when it comes to ventricular refractory and blanking, you will actually not come across a situation where you will have to change it. Typically, it is around 300 milliseconds, the refractory period. And the blanking period is not programmable. It is automatically adjusted by the pacemaker between 50 and 100 milliseconds for the same chamber in a single chamber pacemaker, and also in a dual chamber pacemaker for the ventricular blanking and refractory is like this. So in the last 22 years of my pacing support activity, I've not had a single occasion where I had to reprogram the refractory period for the ventricle. So that means you can understand how rare could that be. But yes, you may come across a very rare situation where there could be a T-wave oversensing where the R wave is too small where you cannot adjust it manage it with sensitivity setting, you may want to change it. Typically, it's the nominal setting, which is 300 milliseconds, around 300 milliseconds. You will actually not have an occasion to change it. Dr. Manish, any?
Yeah, absolutely.
Sir,
I mean, it's only in a dual chamber pacemaker that we change the post-ventricular atrial refractory period sometimes based on whether the patient has got a PMT or something like that. But I'm sure that will be dealt in the next class when Mr. Govind is talking about dual chamber pacing cycles. But by and large, single chamber refractory period, blanking period anyway cannot be, but even refractory periods are kept at nominal settings, no changes.
Yeah, one point you may want to consider is the current, the one that is pictured here, the top of the line pacemaker this actually runs on the ICD platform. So that doesn't have a true ventricular refractory period. It only has a blanking period, which is about 120 milliseconds sense blanking, and pace blanking is 200 milliseconds. And the sensitivity function is slightly different. This might oversense a T wave, in which case we may want to adjust the sensitivity of this system. And again, here you would not be able to program a refractor.
Sir, and what about the sensitivity?
One at a time, please.
In case if any noise occurs, it will reset the refractory period, no, sir?
Yes.
Blanking. And then if the refractory period during that time, if next beat has to be paced, will it pace during refractory period, or it has to wait?
Yeah. As I showed in the slides, where there is a noise, noise recycling happening. If there is a, let's say, electromagnetic interference like noise here, so it starts another refractory, and this one is in the refractory, it starts another refractory. So it will start pacing in this case. You can imagine this as to be a
even during refractory period also it can pace, sir?
Yes. So all the refractory period corresponds to all the ignoring, sensing and ignoring is corresponding to the intrinsic event. If the pacemaker has to pace inside the refractory period, if we have set it in such a way, it will pace during that. So for example, let's take this refractory ventricular sense. It started another refractory. Let's assume this refractory has not ended before the lower rate timed out. So at the end of the lower rate timed out, it will actually pace.
What if it is really an intrinsic beat, then also it will pace?
Yes, it will. If, let's say this was a PVC, and if it happens to be in a refractory period, but if your lower rate times out, the pacemaker will pace you.
Then it will be unnecessary pacing. Also.
Yes, agreed. But that's a very rare instance.
Yes, sir. One more thing. This about sensitivity, sir. What is like a normal voltage, or I didn't get that, sir.
Yeah. So
you were saying that
millivolt. The sensitivity setting is made in millivolt because we want to sense the R wave or a P wave, which is again in millivolt, right? Your typical R wave is about 5 or 10 millivolts, and I want to sense that, right? So just to go back to my sensing, picture. Yeah. So in this one, we have set a sensitivity of, this is my amplitude scale. So let's say I've set a sensitivity of 1.5 millivolts. The fence represents my sensitivity setting. And this one is the R wave. This R wave is about 3 millivolts. So the R wave amplitude is bigger than the sensitivity setting. And every time when an amplitude of the intrinsic R wave or any electrical event is taller than the sensitivity setting that we've made, the device will sense it. Right? So this, let's say, is an optimal sensitivity. So typically the pacemaker ventricular sensitivity is 2.5 or 2.8 millivolts. And that is why we want to get an R wave of 5 millivolts, which means I want to have a two-fold safety margin. The R wave amplitude may change for any patient for a lot of various reasons to some extent. So if I maintain a two-fold safety margin, which means if my R wave is 5 millivolts, and if I set a sensitivity of 2.5 millivolts, I have a two-fold safety margin, which means even when my R wave, if I set it 2.5, let me go to this. Yeah, no, I don't have a 2.5. So if I set it at 2.5, then even when the R wave drops to 3 millivolts, as in this case, it would still sense. But if my R wave is consistently at 2, then 3, then I should not let it at 2.5. I want to increase my sensitivity. That means I need to reduce the number. In this case, let's say 1.5 or 1.6 millivolts. But in order to be very safe, if I increase it to, let's say, 2, I'm making the device extremely sensitive. It will sense the R wave. It might sense the T wave also if it does not get filtered in the electromagnetic. So that's a problem that we may come across.
Yeah. So optimal sensitivity is like around 2.5 we should set, sir. That's best.
Yes.
And
for R wave.
Ideally, it should be your R wave should be at least twice your sensitivity setting. It can be more than that, but it should at least be twice your sensitivity setting. Ideally.
And what about A wave, sir? P wave, sorry.
Same applies. But the P wave typically is 1 to 1.5 or 2 millivolts. Usually.
Okay.
So your nominal sensitivity is 0.5 millivolts for the
0.5 for Atria and 2.5 for RV. So basically what you have to understand is, this one, the pacemaker's main function of a pacemaker is backup pacing. So although many people are, it's a pacemaker, it doesn't pace all the time. It's only when the intrinsic fails that it delivers a backup pacing. So so that's why, because it delivers only a backup pacing, it has got two important functions, not just pacing, but sensing. Both of them are really important. So, what people forget initially, especially, when you're learning is, we have it in mind that pacemaker means pacing. It's not just pacing. Sensing is a very, very important function of the pacemaker to make sure that, it records each and every beat. And whenever there is no intrinsic, it paces. On the other hand, when there is an intrinsic, it shouldn't be pacing. So both these things are very, very important. So understanding sensitivity in a pacemaker is really important to understand the functioning of a pacemaker. So any other questions do we have?
No, sir. One last, sir. So basically, when we interrogate, if we see like a P wave is like around 2 millivolts and R wave is like 5, so we'll keep like 1 and 2.5 accordingly, sir. Sensitivity, or does the machine like automatically regenerates sensitivity, sir? Or we have, yes.
There is auto sensitivity, but I think that will be discussed in the next class. Govind?
Yes.
We can.
If there is, if needed, we can discuss about that. Okay. This one. But generally, we set a cutoff. Like P waves are generally 1 to 1.5. So 0.5 is the nominal sensitivity. So unless the P waves drop and we are not picking up P waves, we do not touch those values. We keep it at nominal settings. Similarly, the R waves also. The normal setting is 2.5 and your R wave is 5 or 8. So we don't have a problem. But if the R wave is dropping, like what was explained earlier, then we really have to look into sensitivity, whether we're going to miss any low voltage R waves. But at the same time, we can't reduce the sensitivity to very low level because you'll be oversensing a lot of other things and in turn get inhibited. Okay.
Okay, sir. Okay.
Yeah.
Yes. Any other questions?
One last question, sir. Sir, one last question, sir. What are the conditions where unipolar lead is more advantageous than bipolar lead, sir?
Epicardial typically are unipolar, and then there are epicardial bipolar also. And it is, most surgeons feel it comfortable doing a unipolar, but then otherwise there is no probably situation where you prefer a unipolar system.
One situation where they used to prefer a unipolar, especially even though you implant a bipolar, so people used to program it in unipolar for only, otherwise, physicians or general practitioners in the periphery would refer the patient back saying that they wouldn't see pacing spikes. So the, pacing spikes are sometimes more evident, in a unipolar lead. So, earlier they used to do that, but right now, most leads are bipolar, and always we do bipolar programming because far more advantageous. So it's only that, sometimes if there is like what was explained earlier also, if there is a problem, the battery is being drained and you're nearing end of life or something like that, and if then you would reduce the rate, and sometimes default it would go into a unipolar programming at that point. Does it go to unipolar programming also at that point?
No,
at DRI? No. Only the rate reduces.
Yeah, only the rate reduces.
Okay, fine.
I mean, it need not be reducing. Even if you are programmed to 50, the Medtronic pacemaker will go to VVI 65.
65, but it will still be bipolar only.
It will remain bipolar and programmed output, whatever you have programmed.
Okay, sir. Sir, I think we'll close, sir. Session.
Yeah.
So thank you very much, and I hope it was useful. So I guess we are meeting on Sunday morning again.
Yes.
Yeah, sir. Sure, sir. Thanks for your time, sir. Both of us.
Welcome. Sure. Thank you, sir. Thanks for joining and giving the
Thanks, thank you so much.
Thank you, sir.
Everyone.
Good time. Good time, sir.
Thank you.
Yes. Thank you, sir.
Thank you so much.
Thank you, sir.
Thank you.
Thank you, sir.